Okay, so this is part 2 of Unit 2. We have 5 minutes. Let's get into it. Yeah, so that definitely did not turn out to be 5 minutes. I'm so sorry. Watch it at your own caution. Now it's like 15 minutes. So, the most important part of this one is that we have to remember the 3 laws of Newton. I'm going to talk about the third law first. So, in this law, it says that force of A on B equals the force of B on A. It's opposite in sign. So, what it basically says is that for all forces exerted on by an object to another object, there is a force equal in magnitude and opposite in direction. It's basically called the action-reaction principle. And then the second law, this one you will use a lot, like in every problem you will use it. So F equals ma. Something important you have to note is that F in question is the net force. It's all the forces combined into one. And it's also net acceleration, which is the same thing where you combine all the acceleration. So the acceleration of a system multiplied by the mass of a system equals the net force. That kind of brings us to the first law, which says that if force is 0, then acceleration is 0. Therefore, the velocity is either constant or 0. So now that we know these principles, we should also know how to do something called free body diagrams. So as you can tell from the name, it's a diagram. And the reason why it says free body diagram is because you get rid of the body. You just use the center of mass. So the first step is you find the center of mass. And as I did here, you find this little dot. And then you put all the forces in as arrows to the center of mass. So all the forces start from the center of mass. As you can see, force of gravity and the force of like normal force. And then now that you have that, you can set whatever coordinates you want based on how you want the problem to be solved. For example, if I'm trying to get the this direction acceleration, like how fast this cube is like falling down this incline, you can basically set the coordinate as this one instead of how you would do for this one. But for other problems, you might have to do differently. So yeah. And now that we talked about those, we should talk about the forces that are causing these. So there's like so much forces in here. There's gravitational force. There's gravitational force, friction force, spring force, resistance force, and circular motion, which is like just centripetal acceleration. So the first force that I'm going to talk about is the force of gravity, and it has this equation. So as you can see from the equation, what matters for gravity is the distance, r, and the mass. If you studied electromagnetism, you would see that it's really similar to how two particles attract each other, but it's basically the same thing, but I don't want to explain it. So basically what we do whenever we're trying to get the force of gravity on an object, we do this. The mass of the object that the object is being attracted to, and the distance between those. So the force of gravity over mass will get this. And that is also the reason why the acceleration on the surface of the Earth is the same for all objects of all mass. Because the mass of the object itself gets cancelled by that. And now that we know that, we can also look at like different alternative scenarios on this. So in this one, we think of mass as consistent, but we can also think of times when mass isn't consistent. So this is called the shell theorem. There's 2 different examples in the shell theorem. The first one is where we think about a planet where all the mass is centered in the shell and inside it's empty. So if you're outside of the shell, we pretend that the center of mass is exerting gravity. But when we're inside the shell, we don't have any gravity in the center of mass, because essentially gravity is the sum of individual forces from the different masses, because masses attract each other. That's basically gravity. So when you don't have any mass in the center of mass, then you won't have any attractive forces at all. So 0 in here, the same as the initial one as here. We just pretend that we do have a center of mass when we're outside of the ball. I mean planet, but still. The next one is where we can dig into planets. We have a planet, and then we dig this much. Let's say it's like L, and then the radius of the planet is like R. When we're digging into the surface this much, we have to get rid of the R as much as the L, and then we also have to think of the mass as decreased because we're only thinking about the mass of the planet in this amount. So you would get the density of the planet usually, but you would have some different mass for the decreased amount of mass. So basically, that was the force of gravity. And the other force is the force of friction. This is pretty straightforward because you just multiply the normal force with the friction constant, which is this. And one thing that's like kind of interesting is that there's static friction and there's kinetic friction. So static friction is what keeps the object static. It's also changing based on the amount of normal force or like the opposing force that you're exerting upon it. Basically what it does is you have an object, you have a not frictionless, friction-full surface, and then you push it, and then the object doesn't move because the frictional force is exerting the same amount of force in that direction, therefore will not cause any acceleration. But there's a time when this force becomes larger than the frictional force. That's when the static friction turns into kinetic friction. And kinetic friction is constant. It doesn't really matter how much force you're putting onto it. So it's pretty nice to put into a graph because if force of friction and time was like in a graph like this would be the point in which the static friction turns into kinetic friction. Because until then, it keeps on rising until it starts actually moving. And then the next one is the force of springs, the spring force. It also kind of has a similar shape, but what's important is that we have these weird things, even though it's like in the same shape of like multiplying two things. This variable is basically how much the spring is stretched or compressed. Basically the change in length, if you will, and this is the spring constant. The spring constant is usually set for the problem. When you're using multiple springs at once, you would do these. So if you're using two springs vertically, you would add the spring constant in this weird manner. But if you're using it horizontally, like this, parallel springs, you're just going to add them together. Yeah. Spring forces are usually very straightforward. It's just that you have to remember that the amount of deformation that happened is this, and you have to take that into account all the time. And then there's this weird thing called resistive forces. So what resistive forces are is they're like a group of forces like air resistance, water resistance. We just call them resistive forces because they behave really similarly. Their characteristic is that it's velocity dependent, which makes it really annoying because you have to do a differential equation. I explained it under here. It's pretty long, I'm really sorry. So what they do is you have the F equals ma equation, and then essentially you know that acceleration is velocity over time, right? So you equate that with the net force, because you know that the net force is, if we're looking at like a falling object with air resistance, it would be mg minus the air resistance. So because we have dv in here, we can technically integrate it and you would get this equation. I really don't want to explain it. You guys already know how to do calculus. You guys know how to do differential equations. Okay, the last portion would be circular motion. So circular motion is basically a thing where an object moves around a circular path. So usually when we're talking about circular motion, we're usually talking about uniform circular motion. So that means that the velocity in which they're circling around this pathway is constant. And what's interesting is that despite the velocity being constant, we need acceleration for circular motion to happen, and that's called centripetal acceleration. So let me just explain that in here. So the reason why you need centripetal acceleration is because the velocity, despite the fact that it has the same magnitude, it keeps on changing its direction. So as time passes, the velocity will keep on moving like that, right? Because it has to move in that circular pathway. So in order to cause this velocity to change into this velocity, you need to like slightly push it into the center. So as I said here, the centripetal acceleration constantly changes direction of the velocity, making the velocity change in direction, not in magnitude. Let's look at a few examples. So that was the most classic one, but there are certain things that we're going to see in different problems. So The first one is, I like to call it the roller coaster problem. So it's when the circular motion is happening vertically. So it has the effect of gravity. So, for example, when the object is on the top, it's different. The velocity is different than how it is on the bottom because you need the same amount of centripetal acceleration in order for the object to keep on staying on the path. So to keep the centripetal acceleration constant, the velocity has to change depending on the gravitational force. So we have to think about gravitational force and its relationship to the centripetal acceleration. So on the bottom, the gravity will decrease the centripetal acceleration. So therefore, the velocity squared has to be probably larger than how it is in other parts. When we're looking at the scenario in which the object is on the very top, the centripetal acceleration and the gravitational force is in the same direction. Therefore, you won't need that much velocity in order for you to maintain the centripetal acceleration because there's gravity also supplying that force. So, because of those factors, when the object is on the very top of the amusement ride, like the vertical circle, we call it the minimal speed because we would need the least amount of speed because the gravitational force is also supplying to the centripetal acceleration. And when we're at the very bottom, we call it the maximum speed because the gravitational force is taking away from the centripetal acceleration. So the next example would be the slanted pathway one. So what's important in here is finding the centripetal acceleration and also perhaps the velocity that causes the object to move so that it won't be dangerous for whatever objects it's moving, so it won't fly away, fly inwards, or perhaps do something else. Most of the time, the centripetal acceleration is provided by the normal force. The reason why is because, as you can see, this normal force gets compartmentalized into normal force y and normal force x. How to do that is through this angle, the theta angle of the slant, being transferred into that angle. So knowing what sine and cosines are, that would be cosine. And cosine theta Fn, normal force, would be the y compartment of the normal force. If we wanted to get the x compartment, which is in the direction of the centripetal acceleration, and is the centripetal acceleration, we would have to multiply Fn multiplied by sine theta. So as I stated here, centripetal acceleration in these slanted scenarios are normal force multiplied by sine theta, theta being the angle in which the slant is being slanted. The y compartment of the normal force is also what's supporting the gravitational pull from the Earth. That's also important because through that we can get the normal force because we know that it's not sinking or soaring upwards into the air. And you would get the normal force through that, and then you would get the centripetal acceleration because we know that the normal force is also causing it. And the next one is, it's when the circular motion is non-uniform, so therefore there's centripetal acceleration and also tangential acceleration. So the last parts, they're kind of confusing looking. They're actually pretty simple. So basically what this is describing a relationship between the period and the frequency. So the large T is the period, and the small f is the frequency. So it's a inverse relationship. The reason why is because a period is how much time it is needed for an object to come back full circle. The frequency is how much circles an object is going to move within a certain amount of time. So what this is how to calculate the period of a circular motion. So you would know the tangential velocity, you would know the radius. This part is basically the diameter of a circle, right? Sorry, circumference of a circle. You divide the circumference of a circle by the velocity, and you would get the time in which it is needed to pass through that circumference of the circle. Therefore, getting the period, which is the time needed to come back full circle. Those you won't need that much, unlike those three examples, but sometimes they would ask you conceptually. The actual last one, are satellites. And these are super duper rare. And basically all you have to do is remember this equation. So the period of the satellite orbiting is this. 4 pi squared multiplied by the radius between the planet's center and the thing that's orbiting it, and then the universal gravitational constant, and then the mass. Those two dividing the whole thing. So that was unit 2. Have fun with that.